Hello students. Today we'll explore a very important chapter in chemistry, periodic classification of elements. This topic helps us understand the logical placement of elements in the periodic table based on their properties. Let's begin with the basics. Periodic classification is the arrangement of elements in such a way that those with similar properties appear at regular intervals. But how did we get to our modern periodic table? Let's look at the historical journey. Doberanner's triads 1817, elements were grouped in threes called triads. The atomic mass of the middle element was nearly the average of the other two. Example, lithium, sodium, and potassium. Atomic masses 7, 23, and 39. 7 plus 39 divided by 2 gives 23, the mass of sodium. Newland's law of octaves 1866. Every eighth element had similar properties when arranged by atomic mass. But it only worked well for lighter elements. Lothar Meyer plotted atomic volume against atomic mass and showed that properties were periodic functions of atomic volume. Mendeleev's periodic table 1869, based on atomic mass. He gave us the periodic law. Properties of elements are periodic functions of their atomic masses. He arranged 63 elements into 8 groups and 7 periods. He even left gaps for undiscovered elements. But there were defects, no place for hydrogen. Some elements like argon and potassium broke the trend. No position for isotopes. Sometimes, dissimilar elements got grouped together. In 1913, Henry Moseley changed the game. He arranged elements by atomic number, not atomic mass. This gave us the modern periodic law. Properties of elements are periodic functions of their atomic numbers. Now we have 18 vertical groups, 7 horizontal periods. Elements arranged by outer electron configuration. The period number tells us the highest principal quantum number. Lanthanides and actinides are placed separately below to save space. Let's break the periodic table into blocks. S block, groups 1 and 2 alkali and alkaline earth metals. P block, groups 13 to 18 nonmetals, metalloids, and some metals. D block, groups 3 to 12 transition metals. F block, lanthanides and actinides, inner transition elements. Let's now understand how properties vary across the table. First, atomic radius. It's the distance from the nucleus to the outermost shell. Increases down a group, more shells. Decreases across a period, higher nuclear pull. Also, remember, cation radius is smaller, anion radius is larger than neutral atom. In isoelectronic species, more protons means smaller radius. Second, ionization potential, IP. It's the energy needed to remove an electron. Increases across a period. Decreases down a group. Group 2 elements have higher IP than group 13. Group 15 is also unusually high due to half-filled stability. Third, electron affinity, EA. It's the energy released when an atom gains an electron. Increases across a period. Decreases down a group. But here's a twist, chlorine has more EA than fluorine due to less repulsion. Fourth, electronegativity. It's the tendency to attract electrons in a bond. Increases across a period. Decreases down a group. Fluorine is the most electronegative element. Let's now explore how specific groups behave. Group 1 alkali metals. Elements Li, Na, K, Rb, Cas, Fr configuration, Ns raised to the power 1. Very reactive, soft metals. Low melting and boiling points. Stored in paraffin due to high reactivity. reactivity increases down the group. Form ionic compounds and monovalent cations. Flame test: Li red, Na yellow, K pale violet. Group 14 carbon family. Configuration: Ns raised to the power 2 Np raised to the power 2. Catenation is strong in carbon. CO2 is linear. SiO2 is a 3D network solid. Hydride stability: CH4 greater than SiH4 greater than GeH4 greater than SNH4 greater than PbH4. Group 2's alkaline earth metals. Elements: Be, Mg, Ca, Sr, Ba, Ra. Configuration: Ns raised to the power 2. Be and Mg show no flame color. Flame test: Ca brick red, Sr crimson, Ba apple green. Hydroxide solubility increases down the group. Carbonates are less soluble than those of group 1. Group 13 boron family. Configuration: Ns raised to the power 2 Np raised to the power 1. Boron is a metalloid, others are metals. Oxidation states +3 and +1 due to inert pair effect. Al is amphoteric. Oxide basicity increases: B smaller than Al, smaller than Ga, smaller than In, smaller than Tl. Group 15 nitrogen family. Configuration: Ns raised to the power 2 Np raised to the power 3. N2 has a triple bond, very stable. Oxidation states -3, +3, +5. NH3 is more stable than PH3, ASH3, or SbH3. N forms various oxides like NO, NO2, N2O. Group 16 chalcogens. Elements: O, S, Se, Te, Po. Configuration: Ns raised to the power 2 Np raised to the power 4. O2 is paramagnetic. Ozone is an allotrope. Acidic strength of hydrides: H2O smaller than H2S smaller than H2Se smaller than H2Te. Volatility: H2O greater than H2Te greater than H2Se greater than H2S. Group 17 halogens. Elements: F, Cl, Br, I, At. Configuration: Ns raised to the power 2 Np raised to the power 5. High reactivity and electron affinity. Oxidizing power: F2 greater than, Cl2 greater than, Br2 greater than, I2. HF is most stable but least acidic. Group 18 noble gases. Configuration: Ns raised to the power 2 Np raised to the power 6, He is 1s raised to the power 2. Inert, monoatomic gases. Xenon forms compounds like XCPTF6. Used in lights, balloons, and medical therapy. Transition elements: D block. High melting points, small atomic sizes. Show variable oxidation states. Form colored compounds. Good catalysts. Example: MnNKMnO4 has +7 oxidation. Photography uses Ag halides with sodium thiosulfate. So students, today we traced the history of periodic classification, explored the modern periodic table, discussed periodic trends, and studied group-wise behaviors. In the next class, we'll solve problems and learn how to predict element properties using their position in the table. Until then, revise well, stay curious, and keep exploring the elements around you. Jai Hind!